So, in our last session we have discussed about potential energy, right. So, we talk about the energy associated with two charges kept at some separation. We also talk about the self energy associated with solid sphere as well as hollow sphere. So, we got these expressions. See, so due to 2-point charges, if I say this is q and this is q and this separation is r, then potential energy expression is q square upon 4 pi epsilon naught r. If I take this one as q1 and this one q2, then the expression was 1 upon 4 pi epsilon naught q1 q2 divided by r, whatever be the separation. So, here separation is r, instead of this r here it will be small r, right. So, for point charges of q1 and q2, u is equal to 1 upon 4 pi epsilon naught q1 q2 by r. In last class I told that here charges must be kept with sign. So, all these values are with sign. So, if they are positive, positive into positive, this will give you positive quantity, potential energy will be positive. If one I take positive, another I take negative. For example, if I take this one negative, so if I put minus sign here, see, if I put this charge with sign, then this whole expression will become negative. So, potential energy will be negative, right. So, positive and negative potential energy, here negative means that forces are attractive in nature and positive means forces are repulsive in nature. I am talking about conservative force associated with the potential energy, right. So, this was the energy associated with 2-point charges. Then we talk about the self energy. For hollow sphere, hollow charged sphere, where charge was uniformly distributed, over surface, we got u is equal to q square upon 8 pi epsilon naught r, where r was the radius and q was the total charge distributed over surface of the sphere. So, we got this expression q square upon 8 pi epsilon naught r. You can also remember this term in this way, q square k times upon 2r, right. So, you can also remember this expression 1 upon 4 pi epsilon naught, I can write k, right. So, by 2 will give you 8 here. So, you can also remember the expression this way, right. This was the self energy, right, self energy, we called it self energy. So, self energy associated with hollow sphere is given by this expression. Similarly, we calculated self energy of solid sphere, where charge was distributed over volume uniformly, right. So, for volume charge distribution, here charge is distributed over volume. So, charge was distributed over volume and we got this as self energy, right, self energy. This is solid sphere. And this you can also remember this way, 3 times q square divided by 3 times q square k. So, this is 3 k, it will make it 5 r. So, you can remember the expression this way also, 3k square 3k q square divided by 5 r. So, this is what we have discussed in our last class, right. Now, see, so based on this one we will see some examples so that this concept will be clear. Let us see first example. So, I have taken two spheres of different radii r1 r2 containing different charges q1 and q2 and charge is uniformly distributed over volume. So, if I ask what is the work done by external agent to make this system, or if I ask what is the total potential energy associated with the system, electrostatic energy associated with the system. So, how much energy is associated with the system? What we can do? So, as you can see that while forming this system, you require only this system. While forming only this system, you require how much energy? Just now we have written the expression 3 q1 square divided by 20 pi epsilon naught r1. This is the self energy of this sphere, right. Similarly, self energy of this sphere, that is 3 q2 square divided by 20 pi epsilon naught r2. So, just making this one you have to do this much work, making this one alone you have to do this much work. Now, you have made this q2 at infinity and q1 at infinity. Now, you are bringing them and placing them at distance r. So, now there is interaction energy associated. So, their self energy, now interaction energy. So, total energy will be sum of self energy and this interaction energy. To find out this interaction energy, I can assume this whole charge is placed at center. Similarly, here I can assume whole charge is placed at center and they are separated by distance r. So, the formula for this interaction, that is k q1 q2 divided by separation r. This is interaction energy and these two are self energies. So, to get total energy associated, you need to add self energies, self energy 1 plus self energy 2 plus the energy associated with the interaction. So, I have just written the expression. If you simplify, self energy of first one we have written here, self energy of second one, this one, and the interaction between these two. So, this will give you the total energy associated to form this system, right. I hope this self energy concept is clear. Let us move to next similar example. So, instead of keeping another sphere out, I am placing one sphere over another sphere, right, this way. Question says what is the electrostatic energy of the system? Now, inner one to solid, this is a solid sphere, so I just want to write the self energy of this one. I can write for solid, I can write 3 q1 square divided by 20 pi epsilon naught r1. This is only self energy of inner one. Now, visualize the situation ki inner one is not present and only outer one is there. Inner one is not present, only outer one is there, right. So, self energy of this one, self energy of this one as this is hollow sphere, for hollow sphere we got formula q square upon 8 pi epsilon naught. So, q square, that means q2 square divided by 8 pi epsilon naught, radius of this one is r2, right. So, q1 energy associated with over q2 energy associated over, right. Now, while writing its self energy, we assume that there is no charge present. So, situation is same as we have created one hollow sphere at infinity and one solid sphere at infinity, and now I am bringing that hollow one and placing it inside the, I am bringing this solid one and placing it inside the hollow one, right. So, what is the interaction energy? Every element of this outer one is at the same distance, you can see from the center of this. So, this situation is same as I am having q1 charge and q2 charge is distributed, brought from infinity and distributed at distance r2. So, every element of this second charge is at distance r2. So, the interaction energy associated with these two is k q1 q2 divided by the separation r2. So, now I have got self energy of this solid, self energy of this hollow and the interaction energy of these two, right. If I add them, I will get the total energy associated. So, self energy of inner one, self energy of outer one, then interaction energy of two shells. Self energy of inner one, I can substitute this term here, outer one I can substitute this term here, and the interaction just now we have discussed. So, all the value if I substitute, I will get the expression in this format, right. I hope it is clear. So, inner one as it is solid, right. So, here you will get this term q1, I am considering q1. So, this is 3 q1 and this will become 5, right. So, this is 5 not 2, right, this is 5. Outer one is hollow, that is why 2 into 4 this will be 8, right. So, this another simple example is clear. Let us see another one. Same as the previous one, now instead of asking what is the energy associated with this one, here I am asking, look at the question, how much work is required to increase radius of this to r1, right. So, what I want to do for this system, I just want to increase the radius of the outer one to r1. How much work is required? From potential energy expression we know that whatever be the work done by external agent, if constituent of systems are not gaining any kinetic energy, is equal to change in potential energy of the system. So, work done by external agent is equal to change in potential energy if the process is done slowly, right. So, slowly we are increasing radius. So, this is valid only if, last class we have discussed, only if change in kinetic energy is 0. That means to get the work done by external agent I require initial potential energy and final potential energy. That I will substitute here, I will get the total energy associated, sorry, total work required. So potential energy final minus potential energy initial is required. Initial potential energy, as the dimension of this one is not given, I do not know the value, right. So I will assume it is having some energy. So this will have self energy, this will have self energy, and the system will have interaction energy like in previous example. So I can write initial energy as self energy of this and the interaction energy between these two. And interaction energy between these two when radius was capital R, then just now we have seen Q1Q divided by 4 pi epsilon naught R. So this is the initial energy of the system. When its radius is increased to when the radius of this one is increased to R dash, now this has become R dash, or in this case it is R1, right. So I will write R1 here. So you can see this its self energy is not changing. So this term will appear again exactly same. Its self energy will change because its radius got increased, and the interaction energy of this one and this one will change. So as the self energy of this one depends on the radius and radius we are increasing, the energy associated will be now less because R is coming in denominator. So in place for final potential energy, in place of R, I need to write R1 here and R1 here. Let us see. So final potential energy U final, this represents initial and this represents final. So final potential energy here, this will get replaced by R1 and this will get replaced by R1. If you subtract these two, this self energy of Q will get cancelled out, and this difference final minus initial will give you work done by external agent, right. So using self energy of sphere, hollow sphere or solid sphere, we can easily solve the problem instead of again considering that small elements are taken from infinity and placed at a particular location, right. So we have already derived the expression for hollow and solid that we can directly use in all such type of situation. So those two formulas are clear by these example. Now let us move to next topic or next example, right. So here question says that we have got one ring, right. You can read the question. A circular ring of radius r with uniform positive charge density lambda per unit length is fixed in xy plane. So this is yz plane. So this is yz plane. Let this be y axis. So this will be z axis. So this is the ring, right. Towards you, this is z axis, this is y axis, and this one is x axis, and ring is positively charged with linear charge density lambda. So this is the setup. Now let us see question. A particle of mass m and charge q is projected from point P, which is root 3 comma r comma 0 0 on x axis. From center it is root 3 r if this point is origin, right. So, let us say this charge q is somewhere here at distance root 3 r from center of the ring. Now question says, what should be the smallest value of v, velocity with which we are projecting it towards the center of ring, so that particle will never return to this particular point. So this point say P. So you have to throw the particle towards the center of ring so that particle never return to this point, it keeps moving like this. And as you know, because of ring, at any point on the axis, if charge on the ring is positive, then force or field will be away from center. So if this charge is positive, because of the field created by ring, it will experience repulsive force. So force on charge, electrostatic force will be like this. Let us write F. So as force is in this direction and velocity in this direction, velocity keep on decreasing, and if velocity becomes 0 before reaching to origin, then particle will take U-turn and again passes through this P point. Particle is thrown towards the center of ring, velocity keeps decreasing. If velocity becomes 0 somewhere here, as force is still in this direction, then particle will take U-turn and moves in this direction and passes through point P again. For it not to reach P point again, you need to provide velocity sufficient enough so that particle can make it to the center of the ring. With almost 0 velocity, if it reaches to the center of ring and it crosses the center of ring, as soon as it comes on this side, force start acting in the same direction. When particle comes this side crossing the center, force on the particle will now be in this direction and velocity in this direction, particle keep moving in this direction and will never come back to the point P, right. So the requirement here is the velocity of particle just become 0 when it reaches here. So when you project with some minimum velocity, condition is velocity at the center will just become 0, right, because after it is having little bit more velocity, it will cross and goes on other side where force will again become repulsive and it keep moving in the same direction, it will never return to the P, right. Any lesser value velocity, then it will move forward direction, velocity reduces, and somewhere here if it becomes 0, then it will take U-turn and will pass through point P. So this is the condition, right. First we understood the condition. Now we will see how many unknowns are there. So there is only one unknown, that is the minimum velocity. That means we require only one equation, right. Now you can solve this problem either by Newton's law, or you can solve this problem by work energy. As just now we have defined potential energy associated, I can solve this problem by energy. So let us see both the methods. Let us see method 1 first. Method 1. Newton's laws of motion. At any general distance x, from here at any general distance x, say this particle is having velocity v in this direction, right, it was projected with minimum velocity, but because of the force in this direction velocity got reduced, and at this particular point it had some v velocity, right. So what I can write for this particular position, force between ring and particle is field produced by ring into charge on the particle. If I divide the force by mass, I will get acceleration. Newton's second law, F by m will give you acceleration. Field by ring, field by ring is charge on ring into x divided by x square plus r square to the power 3 by 2. This was the formula for field due to ring. So I can substitute this one here. So if I substitute, I will get charge on ring into x into this q divided by this m mass x square plus r square to the power 3 by 2. Now you can see that here acceleration is variable. If acceleration is variable, then we cannot use v is equal to u plus at, s is equal to ut plus half at square, and v square is equal to u square plus 2s. As acceleration is variable, we need to integrate to get the velocity. Here what I can write, as velocity decreases with x, I can write this as minus v dv by dx. Acceleration can also be written as a is equal to dv by dt and a is equal to v dv by dx. So this we generally substitute when acceleration either a function of velocity or function of position. So in this situation, as we are getting acceleration as a function of position, we will write this v dv by dx, because if I substitute dv by dt, there will be 3 unknown or 3 variable, d velocity, time and x, but if I write v dv by dx, there will be only 2 variables. So one I can place on left hand side and another on right hand side and integrate, I will get the result, right. That is why I used v dv by dx. So here I can write q ring into this q, right, into x divided by m x square plus r square to the power 3 by 2. Now I will get this term on this side, I will get this dx on other side. Limit, depending on the condition what you require. requirement is velocity at the center becomes 0, that means x is equal to 0, velocity becomes 0. So, x is equal to 0, velocity is 0, and when x was root 3 r, x was root 3 r, here I write root 3 r, velocity was v min. Integrating this one and putting the limit, I will get the velocity v min, right. So, you can integrate this expression, multiply and divide by 2, see. So, if I multiply and divide by 2 here, just look at this term. So, integration of this one will be 2 divided by under root x square plus r square, separately I will write. See, what I am saying is 2x dx divided by x square plus r square to the power 3 by 2, right. If I assume this to be t, this one will become dt, x square plus r square, if I assume this to be t, then 2x dx will be equal to dt. If I differentiate this one, I will get this one, right, this expression. Here I can write dt, so this will be dt divided by t to the power 3 by 2. Integration of this one will be minus 2 divided by under root t, and what is t? What is t? T is x square plus r square, right. So, after integration here you will get minus 2 under root x square plus r square, and with limit 0 to root 3 r. So, this you can integrate, multiply to this term and simplify. Here we are getting v square by 2. So, 2 you multiply and take under root, you will get the minimum velocity. This is one way of doing, right. I suggest you remember this format so that you need not to integrate it again and again, because most of the cases you will get expression in this format only, right, either under root or power 3 by 2. So, you remember that for this one 2 divided by under root t comes, and t is nothing but x square plus r square. Put limit, directly you have result, but you have to integrate, little lengthy procedure. Now, as we have just defined the potential energy, and in the last class I told you that if you use the potential energy expression, you can skip writing the equation for intermediate point, you can directly jump from initial point to final point, as force is conservative in nature, right. So, we can avoid doing integration if we go by second method, that is work energy method. So, let us see second method. I hope first method is clear, that is Newton's laws motion. Now, I am going by energy, work energy theorem I will use. So, intermediate point now is not required, okay, as we are going to use work energy. So, what I can write, there is no external force, work done by external 0. I am writing work energy theorem, method 2. So now this is method 2, right, work energy. So from work energy theorem, work done by external is equal to change in kinetic energy plus change in potential energy. External agent changes the mechanical energy of the system. As there is no external agent present, this term will be 0. So I can conserve the mechanical energy of the system. I can write 0 is equal to change in kinetic energy. Look at this one, final minus initial. Finally particle is here and its kinetic energy is 0. Final minus initial, half m v min plus change in electrostatic potential energy. So 2 particle potential energy we know, 2 particle system potential energy we know, K Q1 Q2 by R. But here you can see that there is a ring and another is particle. One is ring, another is particle. You cannot directly use that formula, right, because first charge here is a distributed one and second charge is point charge. So for distributed one you need to integrate to get the total energy associated with the system. So if I take a small element over here, so I am writing this as Q. Let the total charge on this one is capital Q. Here this total charge is capital Q. So a small element will have total charge, or a small element will have charge dq. What is the energy associated with this element and this charge? So separately I will calculate initial energy associated with the system. So let us calculate separately. Potential energy initial, that is K dq into this Q divide by separation. This is root 3 R, this is R, this will be 2 R by R square plus root 3 R whole square under root, from Pythagoras you can get this distance, that is 2 R. So this distance is 2 R. This is 2 R. So here I can write 2 R. Look at the expression, these all are constant, K, small q, 2 R constant. So if I integrate to get the total energy associated with this ring and this point charge, I need to just integrate this dq. So limit will be from 0 to capital Q, and this expression will become K Q divided by 2 R. This is the initial energy. Now final energy, if I want to write final energy, so similarly I can write final potential energy associated. When this charged particle comes to the center, this gap will, for all the elements, this gap will be R only. That means same expression I will get, but instead of 2 R, now I will get R. So I can directly write after integration, now I am directly writing KQ Q divided by R. So if I substitute final minus initial, so finally this is the energy. I write here K Q divided by this capital R minus KQ divided by 2 R. Now I hope this point is clear. As second charge over distributed one, to calculate the energy associated, what I have done, I have used the integration to get the energy associated. That I substitute in work energy. Work done by external 0. Change in kinetic energy, you know, we have written here. Change in potential energy, after integration we got, right. If I simplify, so this one I hope you understood. I will erase this part. So if you subtract these two, by 2 will come, this 2 and 2 will get cancelled out, you will get V min, right. So here I need to write Q in terms of given parameter, right. What is the given parameter? Instead of total charge, linear charge density is given, lambda. So linear charge density, if I multiply to the total periphery, 2 pi r, I will get total charge. So after simplification, you can simplify, you will get this V min so I hope this application is also clear, right. Here field is non-uniform, you need to integrate. In electric field we talked about situation where charge particles were moving but field was uniform. That day I asked you, if field is uniform what we can do. So if field is non-uniform, what we can do? If field is non-uniform, then by Newton's laws of motion we need to integrate to get the path followed or relation between the parameters, velocity, position, velocity, time and all, right. If it is constant, then we can easily predict the path, that velocity and acceleration, either they can in same direction or opposite direction, path followed will be straight line. But if they are making angle, then path followed will be parabola, right. What if they have, or what if field is non-uniform, like in this case field is non-uniform. If field is non-uniform, then by Newton's law of motion you need to integrate to get the result. So whole concept is clear related to the field, related to the energy. Now let us move to next topic, electric potential, right. So there are basically two ways to define field around charge. One way is the vector way, where we talk about the electric field strength, and using electric field line concept we can tell at particular point what would be the direction of field. There is another way of defining field in the region or space, that is potential. Field at a particular point we absolutely defined, right, but we do not define the potential absolutely at a particular point, we always define the difference. So basically when I talk about the electric potential, I will always be talking about potential difference between 2 points in space. If one I take reference, with respect to that reference I can tell the potential at another point, but whenever I am talking about the potential, it is always the potential difference, right. So let us first define how the potential will be there in space and how to calculate the value of this particular parameter. So the basic definition of electric potential difference in space is, whatever be the change in potential energy when we move particle or test charge from one point to another point per unit test charge is defined as the potential difference. So for example, you are in the field you are moving a test charge from this particular point to this particular point. So, whatever be the change in potential energy of this system, when I say system, it may be a single charge, an external field, it may be a single charge and another charge, another single charge, or it may be a single charge and multiple charges in space, right, or distributed charges in space. So, if there is a field, external field around, and I take a test charge and I move this test charge from this point to this point, whatever be the change in potential energy of this system per unit test charge, that is defined as potential difference between these two particular points, right. So, let us visualize by field lines. So, what I am saying is, if you are interested in finding the potential difference between these 2 points, you are calling this as A and this as B. What is the procedure to find out the potential difference? That you have to take test charge, we have already defined test charge, the test charge must be so small so that it cannot alter the external field. So, our charge must be, our test charge must be so small so that it cannot alter the field what we want to find out, or it cannot alter the potential of, or potential difference between 2 points in space, right. So, I have taken a test charge which I am moving, say I am directly moving from this point to this point. So, whatever be the change in potential energy associated per unit test charge, that will be the potential difference between these 2 points, right. So, this is the definition. So, potential difference between point A and B is change in potential energy per unit test charge, right. Change in potential energy. Change in potential energy can also be written as negative of work done by external agent, or let us first find out the work done by external agent. It can also be written as let us first write in terms of field, then we will write in terms of external agent. So, change in potential energy is negative of work done by field when you are moving test charge from A to B, and you know for a particular condition where change in kinetic energy is 0, this can also be written as plus of work done by external agent. So, you have got these many definition which you can use to find the potential difference between the 2 points in space. You can go by this definition, or you can go by this definition, or you can go by this definition, right. Any of the definition you can select to find the potential difference between 2 points in space, right. So, most convenient is this one. So, generally we will be using potential difference between these 2 points VA minus VB is equal to negative of work done by field divided by per unit test charge, right. So, this is the definition we will be frequently using. So, keep this definition in mind, but you are free to use either this definition or this definition or this definition, right. So, I hope the definition is clear. Now, related to this one, here I am defining potential difference in terms of energy or work. I am defining potential difference in terms of energy and work, right. And for work somehow field is responsible, right, field which is exerting force. field which is exerting force will do work, right. So, that means somehow this is related to the field itself. How these two are related? So, relation between electric field and potential. Relation between electric field and potential. So, this can be written, see, if I use this definition what I told, generally we will be using that definition. So, if I use that definition, then I can write dV is equal to minus work done by field, right. So, when you are moving from point A to B, whatever work you are doing, whatever work field is doing. So, you are moving charge from this point, say point A to point B, right, this way. So, we are following this path. Field in a space is like this and we are following this path, right. Work done by field, force dot displacement. So, force by field dot displacement, F vector dot r vector will give you work, and force is nothing but force experienced by particle in the field. Force experienced by particle in the field is Q into E, right. So, force by field is nothing but charge, in this case it is a test charge Q naught which we are moving. So, this Q naught, how much force it experiences in the field is field intensity into Q naught. So, this term can be replaced by minus Q naught E vector dot dr vector. I use force here, right, divide by Q naught. Q naught will get cancel out. Now, you can see what we are getting is dV is equal to minus E dot dr. So, we are getting dV is equal to, look at this one, dV is equal to minus E dot dr. If we are moving from point A to B, then from A to B potential at A and potential at B. So, actually it is potential at A, potential at B. This is from position A to position B, right. It can be written this way. So, I hope this relation is clear, relation between potential and E. Meaning of this relation we will understand later, right. So, dV is equal to minus E dot dr. What's the meaning of this minus sign? That we will understand later, but this is very important result. So, keep this result in mind. So, using this basic definition, I got this result. So, you can use this basic definition anytime to find the potential difference, but in the situation where field itself is given, this is a better expression to get the potential difference, right. So, I will erase all this. So, basic definition of potential difference is clear, right. I am writing difference here, potential difference, not potential. Now we will understand what's the meaning of this, right. I will erase this one also. I hope you understood the derivation. Now, what's the meaning of this? dV is equal to minus E dot dr. It says that along the direction of field potential decreases. Minus sign here indicate, this minus sign indicate that along the field potential decreases. So, as you keep going along the field, potential decreases. That is the meaning of potential, that is the meaning of this negative sign in potential difference expression. Now, let us first take this. So, in last class I told this is called uniform electric field, right. So, as the gap between lines are not changing, this is called uniform electric field. So, if I take 2 points, say point A somewhere here and point B somewhere here, right. As the field is uniform, I can easily say that field at A is equal to field at B. I am talking about the magnitude. So, magnitude of field at A is equal to magnitude of field at B. What about the potential? Just now we have discussed that along the direction of field potential decreases. The meaning of this dV is equal to minus E dot dr is decrement in the potential when you go by dr distance along the field. Decrement in the potential, minus sign decrement in the potential when you go dr distance along the field, right. That means if I say potential here, I will use different color so that you will be more clear. So, let us say potential here is VA, potential here is VA and potential here is VB. So, according to the concept, along the direction of field potential decreases, right. If I say potential is V, if I go by dr distance along the field, then potential here will be V minus dV. This is the meaning of this expression, that along the field when you go by dr distance, along the field when you move by dr distance, potential decreases by dV. This is the meaning of V is equal to E dot dr. I hope meaning of this expression is clear. Now, I am using this one here. So, as you can see that we are going along the field, potential decreases. So, potential at B will be less than potential at A. So, electric field at A and electric field at B is same, but the potential at B is less than potential at A. Potential at B along the field potential decreases, potential at B is less than potential at A, but they will have the same field. Similarly, if I change the situation little bit, I hope this concept is clear. Just keep this one in mind, that along the field potential decreases, right. Now, if I change the situation, for example, I say we have got this one. This is the example of non-uniform field. You can see the closeness decreases as you move forward. So, the gap between the lines decreases as we move forward. If I take point A here and point B here, then I can say intensity of field at A is more than intensity at B, because here lines are closer and here gap between lines is more. So, this gap is more as compared to this gap, right. So, intensity at A is greater than intensity at B. What about the potential? Along the direction of field, potential decreases. Same concept, along the direction of field, potential decreases. So, potential at A is greater than potential at B, right. So, using field concept, field line concept, I am just checking that in a space which point will be at higher potential as compared to other point, which point is at higher potential as compared to other point. We are comparing 2 points, right. So, field line concept we already dealt earlier. Now, today we are discussing potential concept, right. If field lines are something like this and I take 2 points in a space A and B, you can easily say that here lines are closer. So, electric field at A will be less than electric field at B. What about potential? Concept of potential, along the direction of field, potential decreases. So, when you move along the direction of field, potential decreases. That means VB will be less than VA, VB will be less than VA. So, VB is less than VA for this situation, VB is less than VA for this situation, VB is less than VA for this situation. In all the situation, relation between field is different. Here EA is equal to EB, EA greater than EB, EA less than EB, but the potential expression or potential relation is same in all the cases, right. So, this is most important relation when we are interested in calculating the potential difference between 2 points in a space, right. And look at this one. Dot product, right. If I open this dot product, this is dV is equal to minus E dot dr, right. This can also be written as mod E mod dr cos theta. Now, I am discussing another point. I am talking about this angle between field and the way we are moving, right. We understood the meaning of this minus sign. Now, we are understanding the meaning of this dot product. So, I hope this concept is clear. In all the cases, fields had the different relation, right, but potential had the same relation in all the cases. Potential at B is always less than potential at A in all these cases. So, let us remove all this. Look at this. Say field is in this direction. Just to make you understand, I am taking simplest situation where field is uniform, right. So, field is in this direction and I am interested in finding the potential difference between 2 points, say somewhere here and somewhere here, right. Let us call this as A, this as B, and I am going by distance dr. Field is in this direction and I am going by dr distance this way, and this angle is theta. That means whatever potential difference you are going to get, that depends on the angle between E and dr. So, if you cover same dr distance in different direction, then you will get the highest difference when you move along the field, because in that case this theta will be 0. If I say I need to get highest difference while moving 1 centimeter and there is a field in a space. So, to get the highest difference I need to select the direction of the field to get the highest difference, because in that situation this angle theta will be 0. If I move perpendicular to the field, from here if I go dr distance this way, then this angle will become 90 degree and the difference will be 0. So, point A and point B will have the same potential depending on whether we are covering dr distance along the field, perpendicular to the field, or any other direction. Is that clear? So, if field is this way, and I go by dr distance this way, this angle is 90 degree, then cos 90 will be 0, and what I will write, dV is equal to E dr cos 90, this term is coming 0, that means dV is equal to 0, that means VA is equal to VB. Here potential will be same, right. So, these 2 points will have the same potential, right. So, how much difference you are going to get, that depends on the intensity of the field, and that also depends on the way you are moving in a space. That means the angle made by dr vector with E vector, right. So, I hope everything related to this formula is clear, right from this minus to this dot product. So, this we use when field is given and we want to find out potential difference between 2 points in a space. What if potential is given and you are interested in calculating the field? Potential is given and you are interested in calculating field, right. So, dV is equal to minus E dot dr. I can write, you can see here first, this I am writing in vector form. That means electric field will have x component electric field will have y component and z component. In space, right, dot dr. Similarly, I can write dr in space. So, if this is r vector and you are writing r vector as xi plus yj plus zk, if you differentiate, then you will write dr is equal to dxi plus dyj plus dzk. That means this dr is nothing but dxi plus dyj and dzk. So, this E what I am writing is exi plus eyj plus ezk, and similarly this dr is this one. So, electric field will have 3 component at any point, x component, y component, z component, right. So, when we want to find out field from potential, previous case we have calculated potential from field. Now, I am asking you to do reverse, right. So, you need to extract out 3 component x, y, z. So, you have to see how the variation is in x direction, how the variation in y direction, and how potential is varying in z direction, right. So, one thing is sure that from potential expression we need to extract out information in 3 direction, along x, along y, along z direction, right. So, this can also be written as this way, right. So, if we differentiate v with respect to x, I will get the x component of field partially, right. So, this term is giving you x component, this is giving you y component, and this is giving you z component. So, partially if you differentiate potential with respect to x, this is not dV by dx, this is del V by del x. Partial differentiation of V with respect to x will give you x component of the field. Similarly, partial differentiation of V with respect to y will give you y component. Partial differentiation of potential with respect to z will give you z component, right. So, first one is used to get potential from field, and second one is used to get field from potential, right. If potential is given in terms of R only, like in this situation, say I give you potential like this, V is equal to 2xy square z. So, potential depends on x, potential depends on y, potential depends on z, right. And I asked what is the field in the space. So, I gave you potential and now I am asking what is the field in space. So, to get field in space, just now I told minus differentiate the whole expression with respect to x partially. So, when we differentiate the whole expression with respect to x partially, we have to assume the remaining constant. So, 2y square z, these all are constant, differentiation of x to the power 1 is 1, right. So, this can be written if I differentiate. So, I can take 2 y square z out and I am differentiating x with respect to x, right. Whatever comes I will place minus in front of it. Now, in second term we have to differentiate potential partially with respect to y. So, 2xz is common, 2xz we can take out. Now, we need to differentiate partially the whole expression. So, y square will be inside plus the last one, differentiate partially with respect to z, right. So, differentiate partially with respect to z, I can take 2xy square common and differentiate z with respect to z. Now, this j cap direction, here this one is k cap. I applied this formula, right. If I simplify, then I will get E is equal to minus, this will become 1 2 y square z I cap plus y square differentiation 2y. So, this will become 4, 2y will come, 2 and 2 will become 4, 4 x y z j cap plus, look at this one, differentiation of z with respect to z, right, again 1. So, this will become 2 x y square k cap, right. Now, here I am not specifying ki at this particular point you have to calculate. So, you are getting a generalized expression. Now, if I ask calculate potential at 0, 1, 1, find field at this particular point, find field at 0, 1, 1. So, substitute 0, 1, 1, this will become 2, here this will become 0 and this will become 0, x is 0, x is 0. So, these two terms will become 0. At that particular point you will get E is equal to y is equal to 0, sorry, y is equal to 1, z is equal to 1, then this will become 2 I cap and this minus sign . So, this is the procedure by which if potential is given, we calculate field in the space, we have to just partially differentiate it. Now, sometimes instead of potential given this way, potential might be given this way. So, here we got potential in terms of x, y, z, 3 coordinates. It might be given if I say potential is given according to V is equal to alpha minus beta r square. Now, here it is not given in terms of x, y, z coordinate, directly it is given in terms of r, where r is the distance from origin, right. So, r is the distance from origin. So, if I ask what is the field, E is equal to, then as it is a function of r only, you can directly differentiate, you can directly write minus dV by dr. So, if you directly differentiate, see differentiation of constant will be 0, beta we can take out, r square, right. So, if I substitute alpha minus beta r square here, then what I am saying is this differentiation constant 0, beta will come out, you have to differentiate r square, the differentiation of r square is what? So, minus minus this minus and this minus will become plus 2 beta r. E is equal to plus 2 beta r. What does that mean? That we are getting magnitude only and we can convert this into vector. So, if I want to get this in vector form, E vector can be written 2 beta r cap. So, adding the direction will give me E in vector form, right. So, I hope this one is also clear. Sometime this V might be given in terms of x, y, z, sometime it might be given in terms of r. So, when it is given in terms of r, you can directly differentiate. When it is given in terms of x, y and z, then you have to partially differentiate it, right, to get the different component of field. When it is given in terms of r, then you have to add the direction on your own, right. So, radially outward direction, this is the magnitude of the field. Similarly, so I discussed two cases for field, where I told you that V might be a function of x, y, z, or V might be a function of r, right. What to do? How to get potential, sorry, how to get field for this situation, if V is the function of x, y, z or V is the function of r. Now, if field is given, how to get the potential difference? Let us take one example, so that this concept will get completely clear. So, I will take another example. So, if I say field in a space is given by E is equal to 2xi minus j plus z square k, assume that this is the field in a space, right, and I am asking potential at, find potential at 0, minus 1 2. Now, here I am asking potential. I already told you, you cannot calculate the potential unless until reference is given. So, reference will be given in the question itself. So, reference is, assume potential at 0, 0, 0 is minus 2 volt, right. This is the example based on this one, right. So, I am keeping these two expression as it is, not changing the slide, so that you will have idea that what is the formula and how to apply it, right. So, now I have this and I need to get this, right. Let us apply the formula. So, E dot dr, I am applying this formula, right. So, E is nothing but 2xi minus j plus z square k dot dr dxi plus dyj plus dz k, right, minus limit. Now, we will put the limit later, first let us simplify it. So, I dot I1, I dot j 0, I dot k 0. So, I dot I1, j dot j1, k dot k1. So, this can be written minus 2x dx minus dy plus, I am taking minus out, plus z square dz. If I integrate, here I will get 2 x square by 2 minus y, and then I will get z cube by 3, right. Now comes limit with minus sign in front. Limit, what is the limit? 0 comma 0 comma 0, it is minus 2 volts. So, here I will write minus 2 volt at 0 comma 0 comma 0, and where I need to find out 0 comma minus 1 comma 2, I need to find out potential. Now, if I integrate dV, I will get V upper limit minus lower limit. This side I will get, as there is no space, I am just erasing this one and directly writing what we have got. So, here you will get, after integration you will get V minus minus 2, this will make it plus. Now, look at the limit 0, x varies from 0 to 0, obviously this term will be 0, right, this term will become 0. Next term, y varies from 0 to minus 1, 0 to minus 1, so this term will be 0 to minus 1, and z varies from 0 to 2, z varies from 0 to 2. So, if I simplify this one, then I will get minus, this minus, and here upper limit minus lower limit, with minus minus it will become plus. So, this will be plus 1, and here upper limit minus lower limit, this will become 8 by 3 plus 8 by 3. Now, you can get this plus 2 on other side, it will become minus 2, you can simplify and you will get potential at 0 comma minus 1 comma minus 2, right. So, today we just discuss potential definition and the relation between potential and field, right. Using these definition, because most of the cases we are aware of what is the field created by different distribution. Using this definition or using this derivation, I can find out the potential difference, that we will see in next class, right. So, I hope you understood everything clearly. Try solving the assignment which I gave on this topic, right. Hope you enjoy the class. Thanks for watching.